Hey there, Math 1ers. In this lesson, you will learn how to graph functions with a limited domain and domain of all real numbers. This will be page 9 of your table of contents. So scientists can use a function to make conclusions about the rising sea level. Sea level is rising at an approximate rate of 2.5 millimeters per year. If this rate continues, the function y equals 2.5x can describe how many millimeters y sea level will rise in the next x years. One way to understand functions, such as the one above, is to graph them. You can graph a function by finding ordered pairs that satisfy the function. So for instance, if I ask you to graph the function given, we're going to follow this simple three-step process. I'm going to graph this function given this domain, this limited domain. So we're going to first start by solving for y, since we're given values of the domain, x. So that means we need to manipulate this equation such that y is by itself. So x minus 3y equals negative 6. I'm simply going to solve for y by subtracting x from both sides, and then I'll need to divide by negative 3. So y equals 1/3. To simplify this, remember I can break this apart. This will give me negative x over negative 3. Negative divided by negative is going to be a positive. That's the same thing as 1/3 of x. And then negative 6 divided by negative 2. Negative 6 divided by negative 3 is a positive 2. Alright, so y equals 1/3 of x plus 2. Now we did this to simplify the process in finding these y coordinates. Now, step 2, we're going to substitute the given value of the domain for x and find the values of y. So using this table, I'm going to plug in my x values and get my subsequent y values. When x is negative 3 times 1/3 is negative 1 plus 2 equals 1. So when x is negative 3, y is 1. Pair those together to make an ordered pair. Remember that an ordered pair is simply the numbers x and y such that they will make a true statement when inputted into the equation. And the points collectively on a graph is just that. They're just a set of solutions. So when x is 0, I'm going to plug it in. Y is 2. When x is 3, y is 3. And when x is 6, y is 4. So now I have 4 ordered pairs, pairing the x values with their corresponding y values. Now I can simply graph those on the graph. Remember, this is a discrete graph, it's not continuous, so only those 4 points would show up. I wouldn't connect them because it doesn't include all the fractions and decimals in between. Okay, so you guys try this one. You're going to graph the function for the given domain. Remember to refer to your steps. I give you the domain, so you want to solve for y to start off with. Okay, so pause the video now. Alright, welcome back. So if I'm going to get y by itself, I'm going to add 2x to both sides, like this. That gives me y equals 2x plus 3. Now once we've done that, I'm simply going to sub in my domain values, my x values, into the function 2x plus 3. And I find that when x is negative 5, y is negative 7. When x is negative 3, y is negative 3 as well. When x is 1, y is 5, and when x is 4, y is 11. So given those 4 ordered pairs, now I'm going to graph the ordered pairs. Looks something like this. Now this, once again, this is a discrete graph. Doesn't include the fractions and decimals in between, just those 4 limited points. Okay, so another graph might include, or another function might include an exponent. So let's take a look at what happens when we have exponents and what that might look like. So we're going to still, fortunately this one's already isolated. F of x is the same thing as y, as we know. So if I'm if I've given values of x, I just need to plug them into the function x squared minus 3. So when x is negative 2, remember exponents means we're multiplying the number times itself. So negative 2 times negative 2 minus 3 is 1. Negative 1 times negative 1 minus 3 is negative 2. 0 squared, of course, 0 minus 3 is negative 3. 1 minus 3 is negative 2. And 2 squared is 4 minus 3 is 1. So I've got my subsequent coordinates over here, my ordered pairs. If I were to graph that, you should have this V-looking motion. And I will say that when you have an exponent of 2, which we'll look into later this year, you should have this well, it's called a parabola, this looking this arc, ditch-like figure. Okay, sometimes it's pointing even downward, but as it is right now, it's pointing upward. Okay, so you guys try. We got x plus 2, f of x equals x plus 2. When you want to find you want to ultimately graph the function for the limited domain given. Pause the video now. Alright, so fortunately y is already isolated, so we need only sub in the values for x into the function. So when x is negative 3, y is 11. When x is negative 1, y is 3. When x is 0, y is 2. When x is 1, y is 3. And when x is 3, y is 11. I'm going to take those points, and like I said, this has got an exponent of a power of 2, so we should expect that that parabolic looking thing, and that's what we have here. Yep, this arc. And notice where it intersects the y-axis. I wonder if that has anything to do with this 2 up here. We'll learn about that a little bit later in the school year. Okay, so if the domain of a function is all real numbers, which means it's not a discrete graph, it's continuous, any number can be used as an input value. This process produces an infinite number of ordered pairs that satisfy the function. Therefore, arrowheads are drawn at both ends of a smooth line or curve to represent the infinite number of ordered pairs. If a domain is not given, assume that all domain is all real numbers, or rather the domain is all real numbers. For instance, this is the process we're going to use. We're going to use the function to generate ordered pairs by choosing several values for x. Now I'm going to suggest we keep it simple. We're going to plug in numbers. We're going to make up these numbers to plug into the function to get their subsequent y values. We're going to plot enough points to see a pattern for the graph. 2 points is not enough. Typically 3 to 5 points is plenty to graph a function. And then we're going to connect the points with a line or a smooth curve. For instance, given the function negative 3x plus 2 equals y, fortunately y is already isolated, we're going to plug in some values for x. Now this can be any old numbers for x. I'm going to choose some fairly small numbers because just they're easy to compute. I want to pick some negative numbers and I want to pick some positive numbers, and it's always good to include 0 as well. So let's see. So I've got negative 2, when x is negative 2, y is 8. When x is negative 1, y is 5. When x is 0, y is 2. When x is when x is 1, y is negative 1. When x is 2, y is negative 4. And then when x is 3, y is negative 7. This is 6 points. That's plenty. Again, 3 to 5 points. 5 points is ideal, and you really can use the same numbers, negative 2 through positive 2, as your x values. When you're given, when you're not given a discrete domain. So now, given our order pairs, we got a ton of order pairs now. We can simply plot enough points to see the pattern, and this is going to form a line, of course, and we'll be working on recognizing why we know this is a line. Now, because the order pairs appear to form a line, and because this is a domain of all real numbers, we need to connect those dots and leave arrows at each of them to imply that it's going to go continuously in both directions. This has an infinite number of solutions. Okay, you guys try. You're going to graph the function 3x minus 2. Pause the video now. Alright guys, welcome back. So our answers might vary, but I'm going to plug in our graph should be the same. But I'm going to use, once again, -2, -1, 0, 1, 2, and 3. I get the subsequent points given here. Again, your points might vary from mine, but our graphs should look the same. I'm going to plot enough. We've got another line, and because this is a domain of all real numbers, we have to connect those dots and leave those arrowheads going in either direction. We have an infinite number of solutions. All those little points along that line, all they are ordered pairs, x, y values that if you were to input them into the function would make true statements. And there are an infinite number of them. So let's look at another function with those absolute value symbols. Remember, absolute value means distance from 0. So when I have values, I'm going to plug in some numbers for x here. Just another possible function you might see. Remember the absolute value of -2. How far is 2 from 0? It's 2 units. 2 plus 2 is 4. The absolute value of -1 is 1. 1 plus 2 is 3. When x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. When x is 3, y is 4. Or y is 5, rather. Remember, absolute value is not the opposite. It's distance from 0. And distance from 0 is always positive. Now, if we plot those enough to see a pattern, we should have this V-like motion. Okay, we saw what an exponential graph would look like earlier. Now you're seeing what an absolute value graph is going to look like. Connect the dots and then use the arrowheads to denote going in either direction infinitely. You guys give it a try. Now you're going to come up with a graph for absolute value of x minus 1. Please pause video. Okay, now there might be some variation in the points you chose. I just chose -2, -1, 0, 1, and 2. Gave me the corresponding points. Graph these points enough to see a pattern. We should see that V-like pattern. And then connect them, arrowheads, both directions. I'm going to zip through this one real quick. Now, if the graph is correct, any point on the graph will satisfy the function. Choose an ordered pair on the graph that is not in your table. For instance, if I chose 3, 2 from the graph, I can plug it into the function and it should make a true statement. That's a good way to check your work. Likewise, if I were to give you a graph here and I wanted to use the graph of the function -1/2 x plus 4 to find the value of x when, or I'm sorry, f of x when x is -4, I can use the graph by locating -4 on the x-axis, that's right here, and finding the subsequent value that goes along with -4. So when x is -4, it appears y is 6. So you can find solutions in that manner if given the graph of the function. Alright guys, one more time. You guys are going to find the value of f of x when f of x equals 3. Find the value of x using the graph below. Alright, so using the graph below, we're going to locate 3 on the y-axis because f of x is 3. And you'll see that when y is 3, x is also 3. So that point 3, 3 is a solution, as well as infinite other solutions, but specifically when f of x is 3, x is 3 as well. Just going to look at one other example real quick. Check our work. We can plug in a value from the graph to show that it makes a true statement. And we're good. And yet one more example. You guys can pause and look at it if you need to. Alright, so in this lesson you learn how to graph functions with a limited domain and a domain of all real numbers.